Alright, in this video, we are going to look at the dot product, the elusive thing that I would not talk about in the previous video. You will see how it connects to the previous video in time. We're going to look at work, yes, physics, and connect that to this new idea. And then we're going to look at vector projections, which I actually find pretty challenging. So if you have any questions, just shoot them my way, email, meet me in class, whatever. But I do expect questions there, so don't feel shy. We got the Larson's textbook down here, 839 to 846. They talk about the dot product for 2D vectors there. Yeah, let's go ahead and get started. All right, so I have a box here. And let's say that I want to move this box. Bear with me here. 10 meters. I want to move this box 10 meters to the right. And to move this box, I'm going to apply a force of 50 newtons. I'm going to apply a force, of 50 newtons. Before I go any further, I want you to think, are these quantities vector quantities? All right, we've talked about what this is. This is displacement, and it is, in fact, a vector quantity. And force is a vector quantity. It is in a direction, and it has a magnitude. All right, so we can describe this force and this displacement as a vector. I have a force vector and I have a displacement vector. What are they? Well, this displacement is going to be 10 meters to the right, so I'm going to describe it using the coordinate system as if this were my origin right here. And this is my final destination. Right? So the displacement vector is going to be 10 to the right, 0 up. So I have a vector quantity here. Additionally, over here with the force vector, I'm applying this force 50 newtons to the right. All right, I'm not going to have that end there. But I'm not applying any force in the vertical direction. We only have a horizontal component. So I could describe these two vector quantities with vectors. Here they are, 50, 0, and 10, 0. All right, so my question to you is, how much work is being done? So that requires you to remember the work formula. So the work formula in physics, the formula for work is force times distance. Force times distance. So in this example, we have, specifically, this is the force parallel to the movement. Right? So this force is entirely in the direction of the way we want to move this box. So the work being done here is 50 newtons times the displacement 10 meters, or 500 newton meters, or we have a name for newton meters, 500 joules. All right, but before I move on, I want to connect this to vectors somehow. 50 newtons. How is that at all related to this vector 50, 0? All right, there is a 50, right? But we need to start thinking about how we can connect these two things. How can I connect the 10 to this 10, 0? Right? And it might become clear as I proceed through my examples. All right. And you know what? I'm going to leave it there. Let's go to the next example and see if we can come back to here and connect this 50 to the 50, 0, and this 10 to the 10, 0, right? The amount here to the vector. All right, so new example. I have a box, and I'm going to move this box 10 meters still. All right, but the difference between this one and the last one is that force is now going to be applied in a different way. I'm going to be pushing or pulling upwards at a 45-degree angle, right? So the force is going to be the same. The force is still 50 newtons, right? But this vector quantity now is going to be different, right? I'm pulling to the right, but I'm also pulling up, right? The vector quantity here is still going to be the same for the displacement. The displacement is still 10 meters. The displacement vector is still to the right 10, up none. But the force vector is going to be different. What is that force vector? Take a second to try to figure out what the force vector is. All right, I'm actually going to move where I'm writing my force vector. So if you're taking notes, go ahead and move it, because I do want to put something else there. The force vector I'll put up here. All right, we need to figure out what the horizontal and vertical components are. I want to put a 50 here because we have a 45-degree triangle. All right, and if I construct, to the best of my ability, a 45, 90-degree triangle, I can determine the horizontal and vertical components. So this is 50. What's the horizontal component? Well, that's just going to be 50 cosine theta, 50 cosine 45, right? And then, knowing my right triangle trig, or my unit circle trig, cosine 45, that's root 2 over 2. So that's going to be 50 times root 2 over 2, or 25 root 2. All right, same over here. My vertical component is going to be 50 sine 45, or 25 root 2. So I have my force vector now. It's 25 root 2, comma 25 root 2. All right. So the question now stands: what is the work being done here? So the work being done is we are moving the object 10. So work is force times distance, so 10 meters. Right? But what is the force being done in the direction of the movement? That's 50 cosine 45. 50, and you know what? I'm going to rewind a little bit. 50, I'm going to put the 10 there, cosine 45. I'm going to put that cosine right on the side there. So this becomes 500 times root 2 over 2, or 250 root 2 joules. All right, so in this example, how do these vectors, here we go, 10, 0, and 25 root 2, 25 root 2, how do they relate to the work, right? The x component in both of these is going to be the work that it's done, the product of the x components, right? Because this movement is in the x direction entirely, right? So the vectors, we don't care at all about this y component. We don't care at all about this y component in this example, because all we care about is the direction of movement, and all of the direction of movement is in the x direction. So the vectors kind of uncover the numbers that we care about, right? I was given this 50, but if I had the vector since the beginning, I wouldn't have had to do any calculations. The x component was all that I cared about, right? So the vectors are kind of a more detailed version of the force that's being done. It's not just this magnitude, but it's also clearly telling us the direction. All right, here is my final example. So what is the force that is being done here? We're going to call it F. What is the displacement? D. All right, these are arbitrary amounts. And what I want to do is I want to figure out what the work that is being done here. So what is the work being done? Well, all I care about is the force in the direction of the distance. So I want give myself a little right triangle. I want this quantity right here. Well, what is this quantity? Right? This quantity is going to be the magnitude of the force in the direction of d cosine theta. Right? This vertical, or we call it the orthogonal force, the perpendicular force is going to be the magnitude of F times the sine of theta. In relation to D, we could write this as a vector, F cosine theta, F sine theta. All right? But the work that's being done is going to be the force times the distance, but this force is in the direction of the distance, or the displacement, sorry. And that is going to be the magnitude of F cosine theta. And then down here, the distance moved is the magnitude of the distance. All right, both of these are vector quantities. I should throw hats on those. Right, the force that's being done is a vector. It has a direction and it has a magnitude. The displacement has a direction and a magnitude. All right, so this is the work that's being done. If you give me two vectors, the work that is being done is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them, regardless of the orientation of your system. The angle between them is all that matters, and the magnitude of the forces. Right? F cosine theta is what's going to give you the direction, the magnitude in the direction of the other vector, the displacement vector. Right? We have a name for this in math. We call it the dot product. And the notation that we use is F vector dot, it's a little bit bigger than that multiplication dot that you always used, D. And that is equal to the magnitude of F times the magnitude of D cosine theta, where theta is the angle between the two vectors. Right? What is this in general? Right? The dot product of two vectors, so we're leaving physics for a second, of two vectors, A and B, is, right? We write the notation like this, A dot B, little pretty poorly written vector hat, is equal to the magnitude of the first vector, the magnitude of the second vector, times the angle between them. Notice when we did the basics with vectors, we added and we subtracted vectors, but we never multiplied them, right? And this is why. We have a type of multiplication with vectors, but A dot B is not just like you multiply some random numbers, right? It is the magnitude of the first vector and the magnitude of the second vector times the angle between them. Right? Really important to note that the magnitude of A is a number. The magnitude of B is a number. Cosine theta is a number. You get a scalar quantity by taking the dot product of two vectors. Right? You get a non-vector when you take the dot product of two vectors. Right? In physics, work is equal to the dot product, right? AB cosine theta, FD cosine theta, right? But when we're looking at math, we're kind of removing this real-world example, and we're just looking at the notation, right? A dot B, that's the way we say it, is AB cosine theta, and this is a scalar quantity. All right, so I have a coordinate system here for you. And I have two vectors. Let me go ahead and draw them. I have the vector 2, 5, and I have the vector 4, 1. And I want you guys to find the dot product. I want you to find, let's go ahead and give this thing a name. Let's call this one V. And let's go ahead and call this one over here U. Right, I want you to find U dot V, which means you need to find the magnitude of U, easy enough, the magnitude of V, easy enough, and the cosine of the angle between them. That's probably the most annoying part, is finding this angle right here. All right, but I think you can do it. So go ahead and try to figure out what the dot product of U and V is. Another way to think about this would be to think about if I have an object right here, a point mass right here, and I'm applying a force U on this. What is the work being done? What is the work being done in the direction of V? That's what this quantity is telling us. That's what work. That's what the dot product tells you. The dot product is work. I cannot emphasize that enough. All right. So let's get these things. U, the magnitude of U is going to be the square root of 4 plus 25, 2 squared plus 5 squared. right? And that's going to be 4 plus 25, the square root of 29. Right? The magnitude of v is going to be 16 plus 1, the square root of 17. And now I just need to find that angle. So I'm going to go to a new page to find that angle because the work is a little bit annoying. So I've gone ahead and brought my picture here. And the annoying way to do this problem, I'm actually going to do it kind of this annoying way. I'm going to stop after I declare that it is not the best way. And then I'll do it a little bit better of a way. But the reason why I want to show you the annoying way is because it's very accessible. We just did the law of cosines. And we have the length of this thing. It was, let me just go back and double check my length. It was the square root of 29. There we go. This one was the square root of 17. And I can figure out what this vector right here is. Right? All right. Take a second to think about what this vector is. It's actually not too hard to figure out. But this vector is, and the way I like to think about it is, look, right now, u plus this vector, u plus this thing that we don't know. Let's call it w. It's always nice to give names to things we don't know, as long as that name is nice. All right, so u plus w, I'm struggling to draw my w's right now, is v. Right? This is the definition of vector addition. U plus w is equal to v. Let me go ahead and give myself some hats. So what's w? W is v minus u. This is actually a very useful trick in vector math, vector computations, being able to determine what the vector between two vectors is. W is v minus u. V minus u. And what is v minus u? Well, that's just 4 minus 2, which is 2. And 1 minus 5, which is negative 4. And you know what? It even looks like it goes over 2, down 4. You know, this is just a sketch. It's not perfect, but over 2, down 4. That is w. And what's the magnitude of the w? That's going to be 2 squared, the square root of 2 squared plus negative 4 squared, which ends up being 4 plus 16, the square root of 20. And I'm not going to simplify that because I'm not going to do this whole method. But we can now find this angle because we have a triangle with side, side, side. So we have a side, side, side triangle. And we can do the law of cosines. So I want the angle theta. That's just going to be 20 squared is equal to, what do we got? We got 29, the square root of 29 squared, plus the square root of 17 quantity squared minus those two things, the square root of 29, the square root, oh, don't forget this too. Oh my gosh, that is such a amateur move. Never forget this too. That is where I see mistakes the most. And you know what? I do it too. The square root of 2 times the square root of 29, square root of 17, cosine the thing we want. All right, so just move everything over, take the arc cosine, and then you got theta, yay. And then you can figure out what the work that is being done on an object here moving in the direction of v with a force of u. But there's a better way, and maybe some of you already did it. Let's look at the better way. Ooh, wait, before we look at the better way, let's actually take note that this quantity right here, does that look familiar? Root 29, root 17 cosine theta. Right? That quantity right there is work. That is the dot product, right? That's the magnitude of the first vector, the magnitude of the second vector times cosine theta. So if you are to do this method, you don't even need to find theta if all you want is work. I mean, sometimes you do want the angle between vectors, right? This is how we might do it, right? But we can also grab work out of the law of cosines, right? If I move everything over, divide by -2, that quantity will be work, even though I never knew theta, right? But I do want to segue to the other way because that will then take me to the arbitrary scenario. All right, I want this angle right here. All right, what is this angle? Well, this angle is this large angle, let's call it alpha, and then this small angle, let's call it beta. All right, alpha minus beta is theta. All right, theta is equal to alpha minus beta, and guess what? Alpha and beta are pretty easy to find. All right, alpha is just going to be the angle here, 2, 5, the angle that 2, 5 makes. Alpha is just going to be the arc tan of 5/2. And that ends up being 1.190 radians. And beta is just the arc tan of 1/4. So that's just going to be 0.245 radians. All right, so what is theta? Theta ends up just being the difference between those two, which is 0.945. 0.945. All right, we just did a few things. We were able to find the angle between two vectors. We can just subtract them from the positive x-axis. So we just find the angle of one, the angle of the other, and subtract them from the positive x-axis, smaller from larger. But we also determined what the work is going to be. Where was my slide right here? Right here. It's going to be magnitude U, magnitude V, cosine theta. So the work being done in this problem, the work being done on this point mass right here, is the square root of, I keep forgetting that magnitude. Where is it? There it is. Magnitude 29, magnitude root 17. So 29 root 17 cosine the angle between them, which was 0.945 radians. This is where I say my obligatory, make sure you are in the right mode in your calculator. The work being done here is 13. Exactly. That is real nice. 13 is the work that's being done, is the dot product of the two vectors 2, 5, and 4, 1. All right, let me jump back here. U dot V, which is equal to the magnitude of U times the magnitude of V times the cosine of the angle between them, is equal to, so the dot product of 5, 2, or sorry, no, 2, 5, and 4, 1 is 13. There you go, the dot product in action. So now my goal here is the arbitrary sense. I want to look at the previous example, but with, instead of vectors 2, 5, and 4, 1, I want to look at vectors x1, y1, and vector x2, y2. So what is the dot product? What is A dot B? What is the magnitude of A times the magnitude of B times the cosine of the angle between them, given x1, y1, x2, y2? Can we just evaluate it using those quantities rather than, we want to get this formula and see how it cleans up. So the first order of business, if we're doing this similar to the previous example, is to look at this angle right here. What is this angle right here? Well, since we're dealing with the arbitrary case, we're just going to go ahead and call this angle alpha. All right, I want to stay away from calling it A because we're already using that letter for something else. And then this vector right here has angle, let's go ahead and call it beta. Right, it's like a B with a longer side. All right, so we have alpha and we have beta. That is what theta is, right? The angle between these two vectors, right? This angle right here, theta, is alpha minus beta. So we're already starting to clean this thing up a little bit. Or we're trying to do a little bit of math here. We got cosine alpha minus beta. right? And this is screaming something. Cosine alpha minus beta. Can we clean this thing up? Can we start to make this thing fancier? Right? The answer is, what can I do to cosine alpha minus beta? I'm going to go ahead and write that as cosine alpha cosine beta minus sine, plus cosine sine. All right, we are on our way. All right, I'm just going to go ahead and move this thing over here to the side a little bit because I want that room to do my my algebra here. So the next thing I want to kind of figure out is, what can I do with this cosine alpha cosine beta plus sine alpha sine beta? Well, you may recognize cosine alpha comma sine alpha. Right? What is that coordinate? Cosine alpha comma sine alpha. That is the coordinate on the unit circle with angle alpha. So I'm going to go ahead and give myself a unit circle. Right? This thing is going to have a radius 1. Right? This coordinate right here is cosine alpha comma sine alpha. And likewise, down here, this coordinate right here, this coordinate is cosine beta sine beta. Right? So my goal right now is to think of a new way to describe this coordinate other than cosine alpha sine alpha. If I can get a new coordinate, then I can substitute that coordinate into this equation. Right, so take a second to think of another way to write this vector right here. And this vector right here, other than cosine alpha sine alpha and cosine beta sine beta. All right, go ahead and pause the video and think about that. I am going to proceed now. So this vector right here is a unit vector in the direction of A, and we know how to find the unit vector in the direction of A, right? It's going to be the coordinate in the direction of A divided by the magnitude of A. Right? Down here, cosine B sine B, that can instead be written as x2 divided by the magnitude of B, comma, y2 divided by the magnitude of B. These are the unit vectors in the direction of A and B. Right? But conveniently, these coordinates are also equal to cosine alpha sine alpha by definition. So I'm going to go to my cosine alpha here and replace it with x1 over alpha, the magnitude of A. I'm going to replace cosine B with x2 divided by the magnitude of B. I'm going to replace sine alpha with the y1 divided by the magnitude of A. And I'm going to replace sine B with y2 divided by the magnitude of A. And then I don't want to forget my alpha and beta here. And there we go. There's the money move. Right? These alpha and beta, these A's and B's are going to cancel out those in the distribution process. Right? I'm going to be left with just x1, x2, plus y1, y2. We just figured out that the dot product of two vectors in their algebraic form is x1, x2 plus y1, y2. It's the product of the x components plus the product of the y components. Right? We already knew that A dot B was the magnitude of A times the magnitude of B cosine theta. That's the definition of A dot B. But we now know that A dot B is also equal to, when dealing with vectors in their algebraic form, x1, x2 plus y1, y2, and therefore work, if given the vectors in their algebraic form, is just the product. All right? If I go way back to the beginning, to the physics problems, right? The work done in this scenario was 50 times 10 plus 0 times 0. Right? In my second example, the work done here was 25 root 2 times 10 times 25 root plus 25 root 2 times 0. Right? The work done here, it's the f cosine theta times d plus f sine theta times 0. Right? If I jump to this problem right here that we spent so much time on, the work done is 2 times 4 plus 5 times 1, 13. Didn't we figure out that the work was 13? Where is it? Where are you? The work was 13. 2, 5, dot 4, 1 is 2 times 4 plus 5 times 1, 13. We have just figured out an incredibly quick way to calculate work, given that the vector quantity is expressed in its coordinate form. This will be so useful. I got an example for you here. Find the angle between 6, 2 and negative 1, 8. We can take advantage of the dot product here, right? Because, well, let's give these names. Let's call this U and this V, all right? U dot V is equal to work. Magnitude of U, magnitude of V. Putting hats on all these. Cosine theta. Well, what's U dot V? That's just 6 times negative 1 plus 2 times 8. All right, what's the magnitude of U? The magnitude of U is going to be 36 plus 4 square rooted, so the square root of 40, times negative 1 squared, 1 plus 8 squared, 64, the square root of 65, times the cosine theta. All right, quick formula, if I divide everything here, cosine theta is equal to U dot V divided by the magnitude of U times the magnitude of V. That's what we're using here. All right, so what does theta end up being? All right, the arc, so theta is the arc cosine of negative 6 plus 16. Let's just go ahead and do that. That's negative, that's going to be 10, positive 10, divided by the square root of 40 times the square root of 65. And if I evaluate that, I'm going to get, in degrees, 78.69. Right, this is a very useful formula to find the angle between two vectors. And we now have this new formula for U dot V. It's just the summed product, the product of the first two components and the summed with the product of the second two components. All right, that was a lot of information. I am about to move on to vector projections. So now would be a great time to take a break, turn the video off, go play some video games, or go read a book, or go grab a glass of water, or just power through, whatever works for you. We're going to look at vector projections now. New topic. Let's get started. Let me go ahead and add an S there. We are looking at vector projections. What is a vector projection? Well, let me write out the notation. The projection of U onto V. We are looking for how much of U is going in the direction of V. Right? I always write it out, and I say it as I write it. The projection of U onto V. V is like our basis. We're looking at how much of U is in the direction of V. Right? The vector U is slightly more important. we care about its magnitude and direction. Here, we just care about the direction. All right, we've already kind of looked at this, by the way. Right? A long time ago, we found the magnitude in the direction of a vector when we were doing this box problem. We are also looking at the dot product entirely, but here we looked at the amount of f in the direction of v. Now we are looking for a vector in the direction of v. Essentially, we want to decompose u so we get a vector in the direction of v and a vector perpendicular to v. Pictures will help. I am going to quickly, though, write out the definition. So the projection of u onto v is the component of u that is in the direction of v. So let me go ahead and give us a quick picture. I'm going to have a vector and another vector. And I want to look at the projection of this vector here, u, onto this vector v. So what essentially I'm trying to figure out is, what is this vector right here? How did I get that vector? Well, I like to think of it as, imagine that you have a sun, like the thing in the sky, the celestial body, and it's casting a shadow directly onto you from above, down onto v. Right? This is the shadow of u on v. Right? This is just the perpendicular component. I want to figure out what this vector is. This yellow vector here is the projection of u onto v. Right? So we do have an angle between u and v. Let's go ahead and call it theta. And I think the best way to figure out what the projection of u onto v is to figure out first the magnitude of this vector. We want to figure out the magnitude of this vector. That's a little bit easier to solve for because we've done this before. All right? It's just, so the projection of u onto v is, the magnitude is going to be the magnitude of u, right, times the cosine of theta. Right? The projection of u onto v, this magnitude, the magnitude of this is u cosine theta. That's just a little bit of a trigonometry there, right? But now we need some vector. Let's go ahead and call this vector, like, I don't know. Let's call it a. We need some vector a that has the property that it's in the direction of v. But it can't just be any vector in the direction of v. We need a vector that when you multiply it by u cosine theta, you scale to this vector here. All right. So what vectors have the property that when you multiply them by u cosine theta, you get a magnitude of u cosine theta? You need a vector that has magnitude 1. Because when you multiply a vector with magnitude 1 by u cosine theta, you will get u cosine theta. Right? So A is a vector with magnitude 1 and in the direction of v. What is that? Right? That is a unit vector in the direction of v. We need a unit vector in the direction of v so that when I multiply it by u cosine theta, I will then get a vector in the direction of v, specifically with the correct magnitude. Here's the kicker, though. We know how to find a vector in the direction of v with magnitude 1. We take the vector v and we divide it by its magnitude. We've done this before. Right? That is a unit vector in the direction of v. So here is a formula, and we are going to continue to clean this up. Don't get me wrong. The projection of a vector u onto a vector v is going to have magnitude u cosine theta, and it will be in the direction of v, and this vector here does that. Right? Keep in mind, this is a vector quantity. This is a scalar. this is a vector, or this is a scalar, this is a scalar, this is a vector. So we are going to have a vector quantity. We are going to get a vector in the direction of v with magnitude, the component of u in the direction of v. So this is what we have so far. We have the projection of u onto v is the magnitude of u cosine theta times the vector v all divided by the magnitude of the vector v. All right, this is the projection. Can we continue to work with this? Well, do you know another formula for cosine theta that involves u's and v's? You should, because we just talked about it. Cosine theta, just a note, cosine theta is equal to u dot v all over the magnitude of u times the magnitude of v. Right? If I multiply on both sides by mag u, mag v, I get the dot product formula. So I'm going to go ahead and rewrite this as u. Cosine theta is u dot v divided by mag u, mag v. And then I also have the vector v, and I have a, where is it? A magnitude of vector v. So, my u's and my v's are starting to blend together. U, v, v. Sorry about that. All right, so what happens here? All right, these are numbers. U is a number, so boom, boom, those go away. All right, so the final formula, the one that I care about, is u dot v, that's a scalar, that's a number, divided by v squared, right? We have two v's here, all times the magnitude of v. Right? U dot v all over v squared is that special number that scales v down to the magnitude of u in the direction of v. This is the projection of u onto v. A quick side note, v squared, well, what's the magnitude of v squared? That's going to be v, magnitude of v times the magnitude of v. The magnitude of v is going to be its x component squared plus its y component squared, square rooted. And then if I do that twice, I'm going to get this guy, which is equal to x squared plus y squared, which is actually equal to x times x plus y times y. This seems kind of silly, but that is v dot v. So my particular favorite way to write this formula, this is where you'll sometimes read it in textbooks. My favorite way to write this is u dot v over v dot v times the vector v. So u dot v over v dot v times the vector v. All right. It's funny how at the beginning of this problem I emphasized that u was super important, but look at this final formula. V is everywhere. U dot v over v dot v times v. All right, and that is the formula for finding a vector, finding the component of a given vector in the direction of another vector. Let me just wrap this idea up by writing the formula on its own little page. The projection of u, I've said this a million times, I apologize, onto v is u dot v over v dot v times the vector v. Cool. Awesome. So with that said, I'm going to wrap this up. We looked at work and connected that to the dot product, and we got a really sweet formula for the dot product. x1 times x2 plus y1 times y2. And that connects to the angle between vectors, which I'll let you guys think about why the dot product being 0 means that the vectors are perpendicular. Which we looked at last time. I just didn't give it a name. And then we looked at vector projections, which I find to be pretty challenging. I think I've gotten a little bit better over the years at talking about and explaining why it is what it is. And but if you have any questions, please just send me an email or meet me in class to talk about it. But with that said, I'm going to wrap this one up. And yeah, there you go.